So let's go through an example of Kosaraju's algorithm, the linear time algorithm for calculating the meta graph of strongly connected components. Okay, and so let's start off with the graph that we've been using as a vehicle for our learning so far. And let's start off by calculating the post order numbering of the reverse graph. Because remember, that will give us the vertices that are in the source SCC of the reverse graph, i.e., the sink SCC of the normal graph. Okay? So if we calculate the reverse graph and then run DFS on the reverse graph, we get a post order numbering. Okay? We get the post order numbering of the reverse graph here. And so this is our post order numbering that we'll use in the rest of the algorithm. Okay? So what do we do here? This is our original graph, but we've copied the post order numbers from the original graph. Okay? And what we're going to do is that we want to always find a vertex that is in the sink strongly connected component. Okay, so the way we do that is we find the vertex with the largest post order number. So in this case, the vertex with the largest post order number is 16. So what do we do here? We run DFS on G. It stays in G. There's nothing else that it could reach. So we compute a new SCC that is just G. And then we remove G from the algorithm. Similarly, now we have the new graph with the sink SCC removed, right? So we have removed this, all the edges to it have been removed, and now we have a new sink SCC. That is H. Coincidentally, H has the largest post order number right now. Not coincidentally, that has to happen just by the nature of DFS. So we take H and we can run DFS on H. H can't reach anything, so our new SCC of SCC that contains H is simply the set of just H alone. And then we remove H from the graph, and so we're left with this. Okay. Next, we take the DFS on the next greatest post order number, vertex with the next greatest post order number, that is B. So we run DFS on B, and we can reach E and F. Okay? From B, we could reach E, F, and back to B. Okay? So now we know our strongly connected components that contains B also contains E and F. So we mark that, and we remove it from consideration from the graph. Then we're left with 3 more vertices. We run DFS on A that has a post order number of 6. Then we run DFS and we reach A, C, D. We know the strongly connected component that contains A also contains C and D, so we mark that, and then we remove these vertices from the graph, and what we're left with is an empty graph. So we compute the metagraph of strongly connected components as so, and this is the correct answer, right? So the algorithm looks like this. Find the post order numbering of post order numbering of the vertices running DFS on the reverse graph. We mark all the nodes as unvisited, and then for each node in the computed order, if it's not visited, then run DFS on that node, and let SU be the nodes that run reached by U, and we output SU as a strongly connected component, and we remove it from the graph. Okay, so this together takes O of linear time. Why does it take a linear time? I know it's very tempting to say that this is n loops, and this is O of m n time. Therefore, it should be polynomial. It should be n squared time. But that's not the case, as we discussed. Why isn't this the case? Because we got that little ordering right here. Okay, this ordering gives us extra information. It gives us extra information, i.e., it tells us what order to compute the strongly connected components so that we're always computing a sink first. And because we're always computing a sink first, we're never going to run DFS on the entire graph. We're always only going to run DFS on the nodes that are in the sink strongly connected components. So because we're only running DFS once on all the nodes in the graph, once on each node in a strongly connected component, that's why that this whole algorithm, Kosa-Raju's algorithm, takes linear time. Okay? So we talked a lot about directed graphs, but here's a template for if you're faced with a directed graph problem. Here's a template. Ask yourself if the problem is solvable when G is strongly connected. Is the problem solvable when G is a DAG? If the above two are feasible, then is the problem solvable in a general directed graph by considering the metagraph of strongly connected components? Okay, those are the three questions that we should ask ourselves whenever dealing with a directed graph. Okay, so hopefully that makes sense, and yeah.